Welcome friends to finite element methods for fluid dynamics. We begin this course by first looking at what exactly is computational fluid dynamics and what is high performance computing. So, I just want to give you a small preview of what these two terms are, and then we are going to discuss what will be covered in this course. So, as you are aware, this is a picture of our central library, and this actually came out as a postal stamp on IIT Kanpur finishing its 50 years. So, first let us begin with what is computational fluid dynamics. As the name suggests, there are two components in it, the computing part and the fluid dynamics. Okay. So, essentially we look at models of flow. Okay. These could be equations like the Navier-Stokes equations, and because they are extremely complex, we use computational methods to seek solutions to them. And what I wanted to show here in this slide is some applications, that what is the level of maturity that CFD has reached today, so that we can actually apply this to many settings in our daily life. So, the first picture that you see here on the left, the top left, that is a picture of two cyclists, one behind the other, and this is a CFD simulation. So, suppose you are training for the Olympics and you are interested in asking a question that for the bulk of the race, should you be leading the pack or should you be trailing behind someone to conserve your energy? More explicitly, which of the two cyclists, the upstream one or the downstream one, is spending more energy for the same speed? Okay, as you realize, the downstream guy is in the wake of the upstream cyclist. So, CFD can actually help you answer that. It can also tell you what should be the posture of the cyclist to incur minimum energy loss. It can also tell you what is the optimal spacing between the two cyclists. Okay. It can also tell you about the design of the bicycles for minimal energy loss and so on. In fact, if you look at the headgear, these helmets are aerodynamically designed so that they incur as little drag as possible. So, depending on the posture of the cyclists, okay, these headgears can be designed appropriately. The second picture here is the Formula 1 racing car. As you are aware that these cars, they move at extremely high speed, and in fact when they make a turn, okay, the tires may not generate enough friction in the normal course of design, and therefore the car may skid. So, usually what is done is a wing, an inverted wing is affixed to the car at the rear, and this, unlike an airplane has a wing which produces upward lift to counteract the weight. This wing actually produces a lift in the downward direction. So, that therefore, the reaction from the ground increases, and because the friction is, the force of friction is proportional to the coefficient of friction as well as the normal reaction from the tires. So, because we are producing downward lift, so that adds to the weight and the car produces more friction, and thereby you can have a very safe turn. So, CFD can help you design various components of this Formula 1 racing car. For example, what is the flow through these air intakes? Is that sufficient to run the engine? What about the cooling of the engine? What about the drag on the spinning tires? Is that optimal? What about the person who is driving the car, the pilot? What about his drag? Is that position optimal compared to the intake of the engine? So, there are several questions that CFD can help you answer, and they would be actually less expensive to get compared to wind tunnel tests or actual experiments in the field. Here another picture of the streamlines or the streak lines, or for that matter path lines if you would like, whichever you want, for a similar flow on a racing car. This one is also quite interesting. This is a swimmer who is trying to find out whether the strokes are optimal. So, suppose I have a swimming coach and he would like to find out if I am doing my strokes correctly. So, he can give me a set of exercises and then I can get inside the pool. I can have a team of people who will take my images, actually animated images, and then I could run a fluid dynamic model on it. Okay. So, now that I have my strokes, the imaging of that, I can actually run a fluid dynamic simulation and see what is the disturbance that I am causing to the water. And look at the details. For example, this swimmer, the fingers are completely closed. So, one can actually find out what are the saddle points, what are the separation points as the flow goes past the forearm, what about the flow through the fingers, the web of the arm, and so on. So, you can use CFD even to perfect your swimming and improve your performance. It can therefore be used to design gear, for example swimwear or headgear to reduce drag. Okay. This is a picture of an airplane, a hyperplane. So, there is this question of the air intake which is at the belly of the aircraft, and this has a ramjet engine, in fact a scramjet engine inside it, and one would like to see if the performance is optimal. So, you could use CFD to do simulations and get data where it may not be possible to do experiments. Okay. These experiments would require setting up a huge shock tube or a shock tunnel, and it may not be very conducive to do the right kind of experiments, but CFD can actually give you data. Here is again a picture of a soccer ball. So, as you are aware, the soccer ball goes through a change in design every few years. So, Adidas has the contract for the design and upkeep of the soccer balls, and each year they do a lot of research. So, the number of panels on the soccer ball decide, for example, the lateral movement that a ball may go through, and CFD can help you actually go through this design, what should be the groove size, and so on and so forth. So, how is all this modeled? So, the backbone of all this is a model. Okay. And in this picture I have shown you the incompressible flow equations. So, one can assume that let the flow be modeled by certain balance laws, and what we have shown here is the mass balance, which is simply the divergence free condition on the velocity field, because it is an incompressible flow. The equations would look a little bit more complex if it is a compressible flows. And then you had the force balance or the momentum equation, wherein you have the acceleration term, then the body force, and then these are the surface forces, the divergence of that. And if you assume there is a Newtonian fluid, that is the pressure part, then the viscous stress tensor, which is related to actually the strain rate, and then boundary conditions and initial conditions. So, the challenge here in CFD would be A, to get the right kind of flow model, okay. B, to model the correct geometry. So, we saw examples of let us say the airplane or the F1 formula motor car, or maybe the soccer ball. So, how do you model that geometry, because that is where these boundary conditions would be applied, and then actually then solving these equations for that specific problem. And then that is not going to be easy, because you can see these equations are unsteady, there is a time dependent term here, they are nonlinear, there is this term which is the convection term which is nonlinear, and these are coupled. Okay. So, you cannot just solve continuity equation independent of the momentum equation. So, these are really very complicated equations, and it is not possible to solve them theoretically and to get an answer using a pen and paper. That can be done for extremely simple problems. So, more often than not, you would have to use some computational methods, and in this course we are going to look at one of the methods to solve these equations, and that is the finite element method. Of course, we will look at the details. There are many methods to solve these equations. You could use, for example, the finite difference method, the finite volume method, and then one could ask, why finite elements, or why not finite volumes, or why not finite difference, or spectral method. So, we will when we get into the details, we will try to see how all these methods are related and which one would give you what. So, each method has its own advantages and its own limitations, and we will try to look at those. Now, the second aspect of CFD, which is the computation part, which requires a hardware. So, it is kind of nice to look at the history of or the evolution of computing. So, as many of you may be aware, the unit of computing is called floating point operation. So, if I add two floating point numbers a plus b, that is one flop, one floating point operation. If I add three numbers, then that would be two additions, and that would be two flops. So, one of the measures to look at the speed of a computer is the number of flops, floating point operations per second. So, that is flops. Okay. So, the earliest computers that we are aware of, this is an IBM in 1954, which actually would give you 67 kilo operations per second. So, you can see with the size of this computer, it occupies a big hall, it has all kinds of gadgetry, way ahead of its time in those days. Very few people would get to compute on it, but you can see it only gives you something like 67 kilo operations. Then you move to the control data, and that would give you something like 3 megaflops. Okay, that was really state of the art at that point in time. Then you have the Cray series of computers. So, this is Cray 1 in 1976, which would give you something like 250 megaflops. So, you can see from kiloflops we move to megaflops, and now we are moving to something like a gigaflop, which would mean we are looking at 10 to the 9th floating point operations per second. As you are aware, a laptop would actually give you more computing power than a gigaflop these days. Okay. So, the supercomputer, as they are called, is also a very time dependent term, it is a very unsteady term. A computer which is state of the art today would be a supercomputer, but then 5 years down the line, 10 years down the line, you would find much faster computers, much bigger computers. So, one has to move on and one can solve bigger problems. This was the era of vector computers, wherein you would have a pipeline of numbers and you would operate them one after the other very quickly. So, there would be, instead of scalar registers, there would be vector registers. But then people realized that actually we can do distributed computing. Okay, what that means is that instead of engaging one computer to solve your problem, you can actually engage many computers. But then there is this problem of algorithms, the communication. You know, the example I would like to give is that suppose I request each student in the class to add 1000 numbers each. Okay, so that would be a sequential operation where I give you one number, then you ask for another one, you compute the sum of the two, then you ask for the third number, then you add it to the previous two, then you ask for the fourth number. So, like that you would go through almost 999 cycles or that many additions to compute the sum of 1000 numbers. But we could do something different. So, suppose I have at my disposal 20 students who could add all of these 1000 numbers, and what I could do is I could distribute these 1000 numbers amongst 20 students. So, the first one, for example, would get 1000 by 20, the second one would get the next set of numbers. So, every student has something like 50 numbers. right, and now they are adding 50 numbers each, but in parallel. So, at the end of the cycle, assuming that they add at the same speed, I would have 20 sums available with them. So, each student has 20 values which now need to be added. Okay. So, again I have several ways of doing that. One simple way could be, I would say, well, all of you give those values back to me, and then when I receive them I can add them up and the matter is closed. But I could have another level of parallelism, and I could say, all right, you please pass the values to the guy on the right to you. Okay. So, when that happens, in the next cycle 10 students are sitting idle and 10 of them are adding 2 numbers each, but I have achieved some parallelism. And then in the next cycle I could say, hey, now I will engage only 5 of you and you pass the value to the person on the right of you. Okay. Not everybody, every alternate one. So, there would be some overhead in the sense that there is a communication involved. Also, not everything is in parallel, because I have lost some parallelism. Not everybody is engaged in the activity at all times. Okay. So, I can design special algorithms, and then I can use computers with nice architecture to actually break down my problems into smaller problems and solve them. So, that was the advent of distributed computing. So, there were many computers at one point in time, many companies which tried their luck. So, the one shown here is the connection machine from the Thinking Machine Corporation. So, this is a CM5 installation way back in 1993, which would give you all of 60 gigaflops. Okay. And then we come to the teraflop level. Okay. This, for example, is in 2002, the Earth simulator in Japan, which gave 36 teraflops. So, right now in India we have several installations which have several teraflops of computing power. But then we want to go to petaflops, we want to go to exaflops and so on. So, as you can see, this installation is the Cray Jaguar way back in 2009, almost more than a decade ago, and the rated power is about 1.8 petaflops. Okay. Of course, this is also history, we have much bigger computer. So, the joy of computing is, A, you get more power, and by using more power you can solve bigger problems, you can have more accurate solutions. So, it is almost like a telescope. Okay. If I have a telescope and I want to do astronomy, then the more powerful telescope you give me, the better is my resolution and the more are the structures that I can see in the sky. Okay. Same thing with a computer. If you give me a tiny computer and I want to solve Navier-Stokes, I may not be able to do a very good resolution study. So, you must have heard about the weather forecasts. They are all forecast using weather models which run on a computer. So, I know the weather now and I want to understand what would be the weather 24 hours later. But I would like to make a distinction between what happens here and maybe what happens in Kalyanpur or what happens in Rawatpur or Bada Chauhaya or in Lucknow or maybe what happens in Sydney. So, therefore, the resolution becomes very important, and I can run those big resolutions only if I have enormous amount or sufficient amount of computing power. The problem with having too much computing power are also kind of interesting. A, the bigger your computers, the more is the electricity you need to run these computers. And when these computers run, they generate enormous amount of heat. So, now you need to cool it down. So, it is very interesting. You first run a computer by putting in electricity and it heats up, then you put in more electricity to actually cool it down. Okay. So, it is kind of interesting, you are doing twice the operation of spending electricity. Then when you compute at such a fast rate, you will generate enormous amount of data. So, you need to store that data, and therefore, along with all the computing power, you will need lot of storage capacity. Okay. So, just like you have petaflops in the number of processors, you would now need many disks, many arrays, and now you need to organize the data because this data is also distributed. And then you have to retrieve it and analyze that data. So that also becomes a problem. Space will become a problem. Okay? Then your emissions become a problem, because if you are going to spend so much energy and you are not doing it in a framework of green operations which are environmental friendly, it could come back and haunt you. These days it's a big area of how to pack computers and how to cool them down and how to run a data center efficiently. So it's not just setting up a small computer and doing your CFD. So if you want to do HPC, which is called high performance computing, you are really looking at computing which is state of the art, which is really at a scale which requires something like a center to set it up. Okay, let's look at what CFD can do in terms of huge problems, let's say for aerospace companies. So the next few slides I have borrowed from companies like Boeing and Airbus, which are really at the forefront of making the most ambitious machines, the airplanes. So when you build airplanes, you design airplanes essentially for the purpose of analysis, you have two options. A is to do some kind of a wind tunnel testing. So those of you who are not familiar with wind tunnel testing, let me describe it to you. So if I want to design an aircraft and I want to put engines on it, I would like to know what is the drag or the air resistance faced by this aircraft, because that would decide what is the size of engines that I put in. I do not want to put very big engines and I do not want to put very small engines which cannot pull my aircraft. Okay. I would also like to know how much lift my wings generate, so that I know what is the weight of this aircraft that I can design or I can operate. Now it would be very silly to first make an aircraft, then fly it, then get the data and then say, oops, I made a mistake, let me make another one. So usually what we do is what are called wind tunnel tests. So we make a scaled down model of an aircraft, maybe a 100th model or a 150th model, and then we put it inside a tunnel. A tunnel is something like a room that you are sitting in. So there is air coming in from one end of the room, it goes through the other end, and this is driven by a fan. So this is an example of a test section, as you can see. So air comes in from the front and leaves from behind. Okay. So instead of the aircraft moving, the aircraft is stationary, but the air is moving. So we have done a change of frame of reference. Now by using dynamic similarity, I can estimate what should be my wind tunnel speed or the speed of the air for the given size of the aircraft that I have scaled down to. And then I can put this model on a balance, measure the forces and moments and calculate the coefficients, and then again scale up the coefficients to calculate the forces for my prototype. So that is typical wind tunnel testing. So now if you want to check a different design, maybe you can put in a different wing, or maybe change the location of these nacelles or the engines, or maybe the tailplane or the landing gear, and then generate data which would be useful in design. Now obviously that is going to be very expensive. The other way is to actually model this through CFD. So rather than making a hardware model of this airplane, you actually make a computational model, okay, a CAD model kind of a thing, and then you put a grid around it, do a flow calculation, and then estimate the forces, the dynamics of the aircraft and so on. So whatever information you could get from wind tunnel testing, at least a part of it or sometimes even more, you can get through CFD. What you can also do is that maybe these 3-dimensional high fidelity models are very expensive, okay, they have a very large turnaround time. And let us say I was only interested in designing the flaps and the slats of the aircraft for the time being. So, I could take a 2D section of this wing, for example. So, that is my airfoil section. I have a slat and then I have a flap downstream of it. So, instead of doing a 3D calculation, I could initially do 2-dimensional calculations, and then once I have achieved some kind of an optimality, then I do a 3-dimensional simulation or a few more simulations, and I can then validate that with a wind tunnel test. So, big aircraft companies now what they do is they use all these 3 tools. So, 3D simulations, 2-dimensional simulations, and of course, wind tunnel testing in a loop, so that they can come up with a cheap and an easier way of generating airplanes that are efficient and easy to operate for the airliners. So, how has CFD helped Boeing? Again, this is a slide directly from them. So, listed in this slide are the various CFD tools that they have used. In the 80s, for example, they did not have such high fidelity tools as they have today. For example, now they can do unstructured grids, adaptive, and we'll understand these terms as we go on. So, it suffices to say that with the number of years passing by, the complexity of the CFD tools that they have has increased. So, they are more robust, more accurate, more capabilities to handle complex problems, but they now also need more computational resources. These are the various products that Boeing has produced, the various kinds of aircrafts starting from 767, 757 and so on. And this really is the bottom line. So, you can see in the earlier models they were doing a major amount of wind tunnel testing, that is in the black color, and now in modern times they have replaced this wind tunnel testing with a lot of CFD and very few wind tunnel tests. Okay. So, that should convince you that what is the role of CFD in modern times. So, less testing, and Boeing claims it leads to lower cost, and because you have very accurate results, more confidence, and you can do a more wider analysis for a number of parameters, hopefully you get better products. What about Airbus? So, I thought you would be interested in looking at a competitor which is the European consortium. So, these pictures I have taken from a conference paper by Becker, which was published in 2012. You can find a copy on the internet. So, Airbus has a very similar story. These are the years, the x axis. So, we are talking about all the way from 65 till about 2010, and these are the various products, okay? The 310, the 320, 321, and of course, the jumbo 380, and then of course, the 350. These are the various models that Airbus has been using over the years. So, from very simple models which are potential equations essentially for irrotational flows, inviscid irrotational flows, extremely simple, linear models mostly. Then you graduate to Euler equations, where you are now not restricted to irrotational flows. You can handle rotation a little bit, but still no viscosity as such in the flow, but you may want to fit some kind of a boundary layer or a shear layer code to it. And then of course, the full Navier-Stokes equations in their glory. And you can see the various configurations that they have been able to handle through their CFD over the years. So, starting from simple airfoils to a swept back wing, and you can see there is a shock on it. So, some kind of a transonic flow, to a full aircraft configuration, but this is inviscid. So, you can use some kind of models to estimate the drag and the lift, and then of course, the full Navier-Stokes, which would lead to full flow separation and some kind of turbulence modeling and so on. So, this is what the description is, so these would be simple vortex models and mainly subsonic flows in the late 60s or so. So these would be very small, very simple geometries, and the complexity is at a very minimal level. So we have already shown here something like airfoils. Then you move on to slightly more complex configurations. Now you can deal with maybe some viscous flows, you can add some turbulence models, and finally you can talk about flow separation, more complex configurations, and then of course a full aircraft. So you can see the problem size kind of increases. So you can look at the number of unknowns that you would be talking about. So you are already talking about 1 million degrees of freedom here, and then perhaps something like 1 billion here, okay, and then it kind of gets unmanageable, and you would need very nice high performance installations to cater to these. Again a slide from Becker from 2012, and in this they very nicely talk about what can CFD be used for in aerospace industry. So they've categorized it in these 3 classifications. So something which is used very routinely, something which is kind of once in a while, and these are actually the wish list where you want to use them more often. For example, if you want to look at flutter predictions or a low speed wing design or about the fuselage, okay, belly fairing, nozzles, some kind of deformation of the structure, handling quality data for your simulators and so on. So all that is fairly routine nowadays, and you can use CFD for that. A little less use is when you do wind tunnel experiments, for example, then you need to support your model, and that itself changes the flow. You see, unlike in CFD, which is kind of a standalone model where there is no interference, but if I have to hold a model inside a wind tunnel, then I need to actually make some corrections. So one can use CFD to make those corrections. Wall effects. So if I have a wind tunnel where my blockage effects are large, the walls are too close to the model, those corrections I can make using CFD. Then things like ventilation, okay, inside the cabin, and of course inside the cockpit, and sometimes the electronics, it generates a lot of heat, so cooling that down. Ice prediction, for example, as you know, as you go to higher altitude, you could get ice formation on the wing, and that could lead to deterioration of the performance of the aerodynamics. So how does ice form? What is the penalty that it causes on the performance? The auxiliary power units, their design, ground effects. As the aircraft comes close to the ground, you get more lift generation, and the drag also gets modified, and so on and so forth. And then there are some of these uses which are now coming in a little bit more into practice. For example, the flow control devices, okay, for the next generation of aircrafts. Something to do with engine components, or for example the thrust reversers when you land, okay, and so on and so forth. What is the future according to Becker at Airbus? This is an old slide, as you can see, almost a decade old, so please take it with a pinch of salt, but it does give you a flavor. So the y-axis is the technology performance, okay, and the x-axis is the time, and these are the various aircrafts that have emerged, the devices that the company has been able to pull, and if you look at the trajectory, more or less you would saturate, okay. So the idea is that if you want to get the best aircraft with the thinking that one has, you would have to go for something like multidisciplinary optimization and get this aircraft. But if you want to leapfrog to the next level and get an aircraft which is very high on performance and uses the state of the art technology, perhaps something that is only in laboratories these days, then actually CFD would help you a lot. So if you could do flow control and use multidisciplinary optimization, for example, the wings would deflect, okay, under the air loads. Can we now use that to our advantage? Okay. For example, the tail design, can we optimize that? Can we use the coupling from the engine exhaust and the tails and so on to get a better aircraft configurations? So maybe that would get us to a new configuration. This is again a slide from Airbus just to give you an idea about the performance that is being talked about. So on this axis is actually the available computational capacity in terms of flops. So this is a gigaflop, this is a teraflop, okay, and then a petaflop, exaflop and a zetaflop. And this is on the x axis is the year. Okay. So for example, if you look at something like 2005, we are talking about a few tens or hundreds of teraflops. Okay. If you want to, so this is the curve that we are talking about. Somewhere in 2025, we should be talking about a few tens or hundreds of exaflops. That would be the state of the art. And this is here the various kind of expertise that is available, where the backbone is CFD. Okay. So you can do a full multidisciplinary optimization somewhere in 2015, and what is expected is that when you go to 2030 and you have really the state of the art computing power as projected in 2030, then as a pilot, when I can do the flight simulator testing, I don't run on a database. I actually have a 3D Navier-Stokes solver at the back end, and the computer feeds the data as it would compute on the fly. So I fly the aircraft and I put it in different configurations and I get a Navier-Stokes solution based on the inputs that I give in. So that's really a state of the art flight simulator, and that would be really a boon. Just to let you know, we will talk about this later in the course. These are Reynolds average Navier-Stokes, where you use a turbulence model and then a more high fidelity, which is a large eddy simulation. So a full large eddy simulation for an aircraft is really a dream, and that is expected to be a game changer as far as getting more accurate data for your designs. Okay, just changing gears a little bit, let's go back and try to ask ourselves, how long does it take to generate a mesh on an aircraft and then do a calculation on it? And I specifically chose this slide to make you realize that the first mesh that was reported, as per my knowledge, was in 1978. Okay. But the first calculation, the world's first calculation on a complete aircraft, of course a different one, this is a 747, the 200 version, was actually reported in 1986. So you can see the amount of time between just the generation of the mesh and actually doing the calculation. Okay. So CFD is not simply making a geometry, generating a grid around it and then magically coming up with an answer. There's a lot more that happened in between, and we will of course discuss this as the course goes on. Alright, we will again, I just wanted to give you a glimpse. The equations that I showed you, the incompressible flow equations, they can be used to solve the flow, and we use that via finite element method. Of course, we will do all this in this course, but I just wanted to give you a flavor that those equations have to be cast in a certain formulation, and some technology has to be used so that if you have any instabilities that might come because of computing, they are taken care of, and you are only dealing with instabilities because of the flow. Okay. And then you put this using an algorithm on a parallel computer. Okay. So, here is a picture of a very old parallel computer. This is actually the first parallel computer that I used from one of my projects. This is I am very grateful to the Department of Science and Technology for the support to set up this computer. It was really a game changer as far as our research group is concerned. So, the idea is that in one cabinet you have 32 nodes. So, each one of them is a computer, a rack, a node in a rack, and then there are a lot of cables behind the rack, and all these are computed, they are connected in a certain topology. So, at that time this was state of the art, a gigabit switch, but now of course this is outdated, you would have much faster communication between the nodes. So, you generate a grid like the one I showed you for an aircraft. So, here we were interested in flow past a circular cylinder. So, a grid has been generated, and now you want to distribute computing to each of these processors. So, what is done is you go through what is called a domain partitioning. So, you generate a mesh and then you partition it into, let us say, if I have 32 nodes or cluster processors, I can make 32 of these partitions and distribute one each across them, and they all have the same number of unknowns, so that they have roughly the same amount of work and they will all get done together. What I want to do is minimize the communication between these different nodes. So, for that I minimize the number of nodes that these partitions share with each other. So, the information that is needed between these partitions is really only at the boundary. So, if I just scattered the nodes randomly across this computer, then everybody would need all the information because they need information from the neighbors. But if I do it in this smart way, then I only need to communicate between these processors the individual neighbors for each partition. Anyway, we put this on a computer, and there was an algorithm to parallelize this, and a method was used to solve these equations, and there are some libraries that are used, the message passing libraries. And typically we store data at 3 levels, okay, in a finite element program. So, we will talk about this in more detail. So, if you look at this mesh, these points where these edges intersect, those are called nodes, and as you can imagine, each one of these little regions is called an element. So, we store data at nodes, at elements, and at the equation level, and then we kind of go back and forth between these data structures. Mantra to keep in mind is that computations are fast, but communication of information is slow and expensive. That is because the computers are becoming faster. So, if I want to compute, that takes less time, but if I want to convey information between various nodes, then many would have to wait, and therefore that is slow. So, this is one thing that we keep in mind. In a typical finite element program, okay, you will see that most of the time is spent, almost 80% of the time is spent in just solving the linear equation system Ax equal to b, and very little time is spent in communications, almost 10%. Okay. Okay, this is a picture of one of the older clusters that we had at the computer center. Now, of course, we have a brand new installation coming up, but let me just share some information about this setup. So, this one had about 372 nodes, computing nodes, and on each node there are certain cores. So, there are roughly 3000 cores, and because this whole machine is a central facility, each user can only use up to 640 cores. Okay, this is just to have equitable distribution of resources, and this is the spec of each of the processors, and the nodes are connected by an interconnect. So, that is a 40 gigabit per second, it is called InfiniBand. Now, what we want to do is take a problem and then see how it scales up. So, if I take a particular let us say flow problem and I run it on just one core versus I run it on 2 cores, 100 cores, 500 cores, it should speed up. In fact, it should speed up in an ideal case linearly. So, if I have 100 cores or 100 computers, then it should take 1/100th the time to solve the problem. Okay. So, the next slide I want to show you some speed up studies. So, we took a problem and these are the various mesh that have been used to solve that problem. So, these are the number of nodes and elements and the equations. For example, M1 is the coarsest mesh that has about 2 million grid points, which leads to about 17 million equations. So, these are solved, these nonlinear equations are solved at every time step. The finest mesh has about 47 million nodes, okay, and it has about 370 million equations. Okay, so, something like a 0.4 billion equations, and we want to see how fast this thing scales up on a computer. So, x axis is the number of cores that we are using and the y axis is the speed up. So, speed up simply refers to if I run a problem let us say on 200 cores, then speed up means compared to if it was running on 1, what is the fast rate that I get on 200. Okay. So, as you can see, if I look at the coarse mesh, the M1, so it scales up to some point, and then beyond a certain point if I increase the number of cores, it does not help me. Okay, so, it is the same problem as I alluded to earlier in this talk, where I said I would like you to add 1000 numbers and there were 20 students. Now, suppose I say there are 1000 students and 1000 numbers. Okay, you can see that parallelism is not really going to help so much, because I distribute 1000 numbers to you, each one gets one number, there is nothing to add, and then you just communicate to your neighbor. Okay. So, the performance actually starts saturating after a certain number of cores. So, for this problem, if I use anything more than let us say 200 or 250 cores, I do not really gain so much. On the other hand, if I go to this fine mesh, now you see I can get higher performance by using more number of processors. So, the idea of this table is that when I want to solve a particular problem, I can actually run this test and see what is the optimal number of cores or processors that I can use. Conversely, the bigger the computer I have, the bigger is the problem that I can solve. Okay. So, today if I can do with my computer let us say flow over half a wing, maybe if I get 10 times the computer, then perhaps I can do flow past a full aircraft, as an example. So, this is pretty good scaling. The red line is the ideal scaling, that means with 700 cores I would get a speed up of 700. That is ideal, you would almost never get that. Okay, but look at our codes, they are actually scaling quite well. So, using these codes we have been able to do a set of problems, and I just thought it would be a good idea to just give you a flavor of what we do with these finite element analysis. So, this first problem here is actually flow through an intake of an aircraft. So, as an aircraft flies, the engine needs air it is called an air breathing engine. And the engine, actually you put in fuel in it and burn it. So, there is a flame that is there in the engine which is responsible for the combustion. But you want the airflow speed inside the combustion chamber to be small. If it is too large, then you can imagine the flame will blow away. So, the idea is when an aircraft is moving at a fast speed, so you can see this is the engine, the center body of an engine. So, as it is moving forward, the air should come in, and wherever combustion takes place, it should slow down. So, we want to convert the kinetic energy of the flow into high pressure and in an efficient manner. So, these are some calculations that were done to understand the instabilities that could happen in an air intake. These are some very canonical problems about transition of flow on bluff bodies. So, this is a circular cylinder going from one wall to the center of the wind tunnel, and we want to understand vortex shedding and the related transition. These are actually vortex induced oscillations. So, when you have unsteady flow on these bluff bodies, they can actually vibrate because of the forces acting on them. So, we have been able to do some simulations to understand that. This is a problem in transonic flow on airfoils. So, where you could have shock boundary layer interactions. This you saw an example from the picture in Boeing, where these are high lift devices. So, we have the leading edge slats and the trailing edge flaps, and the idea is that when an aircraft is about to land or take off and you want to generate additional lift, these devices are used. This is high speed flow for a bluff body, and you can see the shock structure here, and of course also the shocks in the wake, but they need to be resolved well, and typically what is done is a finite element mesh is adaptively refined so that you get a higher resolution near the shock. So, the mesh itself depends on what the solution is. Okay, so, that is called adaptive gridding. This is a picture of flow past badminton shuttlecocks. This one is a duck feather shuttle, and this one here is a synthetic shuttle, and we are interested in finding out how different the flows are which cause different trajectories of these shuttlecocks. Here is an example of a ram air parachute. So, as you are aware, parachutes are roughly of two kinds, the round canopy one which generate drag, but then there is also something like a wing, a ram air parachute, which can actually glide and do a targeted delivery. So, we have done some analysis for those parachutes. This is a project that we had from Indian Railways to see what can be done to retrofit engines if we have to increase their speeds. Okay, Indian Railways has plans to increase speed of all its locomotives, and this was an exercise to investigate the pressure drag. This is actually a flow over a wing of an aircraft, a transonic flow. So, we were interested in looking at the shock boundary layer interaction. These are some studies to look at transition because of the laminar separation bubble on an Epler airfoil, both in 2 dimensions and 3 dimensions. And this one is flow through a complete wind tunnel. So, if you want to design a supersonic wind tunnel, these simulations can help you with that. So, this is just some of the problems that have been computed using these methods. One can also use these methods to look at coupled problems, and I want to show you one example of the case of a fluid structure interaction. Okay, so, although this course is mainly about fluid dynamics, but I thought you would be interested to see a situation where there is an interaction between the fluids and solids. So, this is a toy problem, just to give you a flavor. So, there is a cylinder which generates an unsteady flow, and attached to it is some kind of a flexible plate, a filament, and then because of vortex shedding, this filament can vibrate. Okay. And this picture actually shows you how this is being handled computationally. So, you can see the challenges here. The geometry is changing, but not in a prescribed manner, that is part of the solution. Okay. So, there is a very tight coupling between the flow and the structure. So, we have to solve the equations for fluid mechanics, we have to solve the equations for solid mechanics, then there is a grid, and this gridding has to be done dynamically on the fly as the body deforms. The loads from the fluid have to be transferred to the structure, and likewise the deformation and the velocities that you get on the structure, they have to be transferred back to the fluid. Okay. So, we have done many other problems. This was just a test problem for fluid structure interaction. Anyway, I would like to stop here, and I hope you have got a flavor of what CFD is and what high performance computing is. And in the next session, we would like to see what exactly we would be studying in this course. Thank you very much.